So they are asking for suggestions. Yes, exactly. Yeah, exactly. Hey, look. This will be avoided. Oh. Hello.
Hello. Yeah, okay. Welcome everyone to this third day. It's exciting because we're going to have the hackathon. But first, I would like to ask Anand to say a few words.
Good morning. I don't know, this is now become formality that somehow we have to come and give some speech. But anyway, I welcome you. Good morning to start with. I hope you had a good time discussing or understanding what can be done with AI and machine learning algorithms. And a person who trained from classical astronomy, this is all amazing to me because my life itself, several things have changed. During PhD, if you get one high resolution spectrograph, and that is work for quasar spectrum, that is work for 3 months to 6 months for a PhD student, because we will go through each and every pixel and identify lines and fit them, kind of, and you will be surprised when we did publish the first spectrum. That was the 4th spectrum published ever. So I remember publishing one detailed analysis. It took 6 months to analyze one spectrum. Then when my PhD students start doing their PhD, they were doing about 100 spectra, kind of. That is their benchmarking, 10 years down the line. Then what happened, next generation, my students, actually it has happened. The same thing, but they are analyzing now several hundreds or thousands of data from SDSS, but in a computer-based way. I will not call it as machine learning or something. It is like brute force. Whatever we manually do, they do it supported by statistics. So what is puzzling now is the latest student in that branch. They are now doing something interesting. They do no more do fitting. And they say, like, you give any spectrum, we will tell you what it is. So that is the kind of evolution I have seen. So while I keep joking, which is true also, I will tell the same thing. Before you want machine to learn, you must learn physics. Otherwise, you don't know what the machine is telling you. So I think that I am sticking to. Just I realized, since it is also, you are also asked to think about usefulness of these things in astrophysics and what kind of things you want to address. I think that's what you guys are going to do today, if I understand correctly. I'm just seeing what all I think AI is doing now. Kind of, it gave me an opportunity to scan through publications to see, and also future projection to see how things are done. And one obvious thing is that this is what is being highlighted in any of these advertisements. It's like you have large volume data. You want to do various things. You want to identify objects. You want to quantify morphology. These are all routine things, I would say, nowadays. It used to be challenging in the past. These are very routine thing. And what is exciting to me is that the second part. See, having done data, having obtained data, astronomy data alone is fairly useless. This is a very strong statement. It is useful for only people who are looking for correlations. But if you want to extract physics, what you will do is that you will end up having some physical model and try to reproduce your model with observations by varying parameters. So our ability to extract physics in that way is limited by computing power and your algorithms you are using. What is heartening to see now is that usage of AI and ML has changed the whole scenario. Now, for example, in cosmological simulations, if you ask distribution of matter, we were doing standard one-dimensional statistics, correlation functions, whereas the actual distribution is completely complex. You see that it's cosmic web or this and that. And I noticed that now we have moved out of, are slowly moving out of this correlation function-based analysis. We are looking at patterns and you are treating them like exactly what it is, right? It's a field and the evolution of the field and structures and whatever. So that is a great achievement. So why I am bringing it in is that in the initial stages of your learning, machine learning, you are always introduced to statistics and other things. I will urge you, if you are really keen in pursuing high level A&A, it is important that you spend time on integrating this computing part into data analysis, because I think this will be the cutting edge part. Otherwise, you identify supernova, somebody else will identify the same supernova. I mean, a better example will be, I know that people try to get quasar candidates in SDSS. Okay, you will find 10 more quasar candidates by doing this, but I think it's a differential improvement. Whereas if you can do physics-based extraction of parameters using innovative ideas, it's difficult, but we have to do difficult things, right? That's the last bit which impresses me again is that recently I hear talks where people are saying how you can operate observatories with AI. There are two things which you can think of. One is that intelligently deciding what to observe. So observatories can decide on the fly what to do, because that is again, I think transient fellows have mastered it for a period of time. What I think will be more interesting is that look at TMT or look at LIGO. See what happens is that sensitivity depends on how various subsystems are performing. Are they performing to the optimum level? What we usually do is that a human being will sit and keep looking at the monitor and fine tune. For example, some misalignment is there, they will try to do it. If the whole thing can be done in an intelligent way, say some prediction is there, if something is happening, some other pattern will happen, and if you do it, it will save a huge amount of time. A human being will have a time scale of a few minutes at least. So keeping a stability of an image, if it can be done with AI, and I noticed that it has been done in LIGO, not LIGO, in gravitational observatories, where people are able to lock lasers over a long period of time from taking information from sensors and other things. So what is the point of me giving talk here? I'm just telling that younger people, you just think of data mining and this thing, but AI has much deeper, this is what I'm learning also, much deeper application which cannot be done by human beings at the time scale at which AI can do. So I hope it's a good initiation for you, and these guys are experts, and please get in touch with them and continue to grow, because this community has to grow, not only AI or ML or astronomy per se, we have to grow the community by huge amount, because you people are extremely lucky. Because by the time you are mature enough to do independent research, India will have access to best facilities in all wavebands. This thing we never had. We have to depend on foreign collaborators to get data, or we have to depend on archival data to perform things. So I wish you all the best, and having come to IUCAA, I hope you also have some time to discuss with other people around and see like what kind of astronomy is going on here, and then decide how you will apply the techniques you learn in various aspects of it. Thank you very much.
I can go, otherwise I have to code.
Thank you, Anand. Thanks for taking out the time. Okay, great. So then today, as I said, we're going to start with the hackathon. This is the picture from yesterday. We have also taught Newton to do some machine learning, I guess. So what I had suggested is for people to put in slides regarding their projects.
I think I see a few more projects which were also highlighted, which may not be on the slides here. That's fine. But let's go one by one through these projects. We will give like a few minute introduction to what this project is about, the science goals, and then what kind of data sets are available, etc. After that, I will try to give you a short demo of what this Sci server is, and I hope some of you have at least gone through it. And if not, I hope that whatever demo I give, that at least gives you a rough idea of how to get started. And then we will also, Asitan will tell us about how to take project ideas and then try to get it to a mature kind of a project. So that's basically the goal. What I'm also going to do is I'm going to send out a Google form link so that you can write out your email address and tell what project you are interested in and what your Sci server user is. So what will happen is that will help us to keep track of who is doing what. And more importantly, on Sci server, all of us don't need to download the same data at the like in our own directories. It will help us to share this data with each other, so that only one person per project group needs to actually download this. Okay? So I will send this out, but just keep an eye on which project numbers you would be interested in, because it will take some time for me to send out this Google form. Okay? Okay, so let's get started. First is Jitendra.
So couple minutes per description.
Yeah, few minutes. Yeah. Couple. Okay, yeah. We will cut you off if you go more than two.
Yeah, hi, so my name is Jitendra. I've been
Can you use this? Get recorded.
Will it be easier to
Or this mic. Yeah, use this.
Then you will have it.
Hello? So, it says mute.
Meanwhile, you can use that.
Yeah. This one will be that.
Can you hear me? Okay, so I've been working on AstroSat CGTI data. CGTI is basically an imager, hard X-ray imager on board the AstroSat telescope. It stands for cadmium zinc telluride imager. What we have been doing here in IUCAA is also detection of GRBs in this imager. So the way we do detection in these instruments is by okay, I hope I'm audible again. Sorry. I think it's fine right now. Okay. Yeah. So the way we do detection is by two methods. One is we get this GCS, we get these circulars out from other instruments such as Fermi telescopes, and we go and look at that given trigger time to see if we have detected a GRB. And the second method is blind triggers. We just use different methods to different ways to look for these GRBs. And one of them is there are a few of them running, one which uses machine learning, one which uses some other algorithms and all. But recently we have developed an algorithm called sum threshold. Like we have used the sum threshold algorithm to detect GRBs. Like sum threshold is mostly used in radio. If you're in a radio radio persons here, they would know better, but we use this SMT algorithm to detect these GRBs, which are shown to show very promising results. But the problem is it also detects a lot of noise, which is, I mean, it's a good thing and a bad thing. So just to give you an idea of what this, like basically we'll get all kinds of trigger. The data set is basically the CGTI data, which is around the 7 to 8 years of data, which has, like, till now we have detected 600 GRBs and all. So I have ran this algorithm on these around 550 GRBs, and it has shown to detect 500 of them. And as we are speaking, it's also running in the background. As soon as we get the data, this some threshold algorithm starts looking for a GRB. And recently it detected one of the faintest GRB we detected by blind search. So usually if we get a trigger from, say, Fermi telescope, we do go and see if we have found if we have found a counter match in our CGTI data. Most of the time it's very faint, as you can see here. It's not really visible, but we just send it out saying, okay, we can see some spike, and basically then do the more analysis on this. But now the sum threshold algorithm has only been performed for 2 to 3 months and have shown to show very promising results. But as you can see, it shows a lot of noise. So this is definitely some noise. You can also see here it got some trigger here, which is also some noise. So basic what we are thinking of. So I'm also new to all of this, to this GRB analysis and all. I've recently started looking into this. So our main goal is to differentiate between this noise and GRB, which I thought from basically these 2 days of lecture can be very helpful in basically understanding what I can do further. So it's more of a learning for me as well. These are some other examples. So one more thing is we get these solar flares as well. So as you can see, this is a GRB, this is a GRB, but this is a solar flare. Now, how do we know this is a solar flare? Is we cross-match it with the solar telescopes that we have. There's one on Chandrayaan-2, I think. So we use all of these catalogs. We see if at this trigger time there was a solar flare. If there was, then we say it's a solar flare and not a GRB. So also differentiating between these two would be interesting. Just one small quick last thing is, one thing in GRB is that you can see this exponentially decay feature, which you usually don't see in solar flares. There is something which can be done with this as well, the differentiation between solar flare and GRBs. So yeah, this is basically what I wanted to show, what I'm trying to do, and maybe some help would be great. Yeah, so.
Here guys, to share this screen. Okay. Any questions? So I had one actually. So do you have labeled data for some of this which you have uploaded on SciServer? You have to start.
Yeah, I have to start because it's a huge data set. 7 years, it would be terabytes as well. So
Okay.
It's a bit confusing. It was a bit confusing for me on what to upload.
You may not need all of it.
Yeah, I'll upload
so just
some data.
some examples with labeled data.
Labeled data, sure.
Yeah. Any other questions? Okay. If not, before I talk about the project that I just wanted to tell you about this other URL. So DSW 2020. That's always the common thing. And then after this, it's project choice. My handwriting is not so good. P capital and C capital. Project choice after DSW 2020. You will get a Google form, and that you can use in order to choose which project you would like to. Okay. Then.
Hello. Yeah. Okay. So the next thing
is something that I have put together. So for the last quite a few years, we have been working on this project related to finding planet 9 in our solar system. And in order to do this, you have to do something called difference imaging. So let me explain quickly what that is. So you must have seen cartoon pictures like this, where you have to find what is the difference between these two pictures. You must have played this as a child. So if you just do a simple subtraction, then everything that is different just pops out, right? So I was telling my daughter yesterday to do this, and then I showed her this. So you can count all the 10 differences then very easily. So something like this, we also have to do in astronomy, where yeah. So you get two images, one on one night, the second one on another night, and you want to know whether things have changed between them. So if you want to identify transient sources, variable sources, moving objects, this is something that is important. So you have a template image and a new image, and then you want to know whether something has changed. So if you do a night difference, like what I did in that picture, then you get these kind of donut-shaped objects. This is because the atmosphere is blurring the images every time you see them. And the blurring is different on different nights. And so because the blurring is different, you end up seeing these kind of donuts. Okay? So there are different imaging algorithms that have been developed in order to make sure that you match the PSFs or the point spread functions in each of these images and then do the difference. So these algorithms such as Allard-Lupton and then Zogi, which was shown previously, they do a PSF matching of these images before subtraction, and then they carry out the subtraction. Now the problem is when after you do the subtraction, you get rid of a lot of the things in the image which don't vary. Okay? But when you do the subtraction, oftentimes, and if you carry out source detection on these images, then oftentimes it can result in lots of false positives. So in addition to identifying things that have changed, you start to also see a lot of false positives. So what are these false positives? Sometimes you are near stars, and the stars have some saturation trace, and sometimes they have things which flare out in the images from them, and these also get identified as difference imaging sources. And so what we would like to do is to try to distinguish the real sources from this junk that gets detected. And this is a large number. So for things like LSST, which is an upcoming survey that is going to happen, start in 2025, the number of objects that get detected on the difference image compared to what is real, the factor is about 1 in 100 or so, which is real. So getting rid of all of this junk is something which is important. And so the main goal of the project is to go from cutouts of difference image sources. So cutouts like this, classify things which are real transients or moving objects and separate it out from junk. So that is what I would like to do. The available data is fits cutouts around difference imaging sources that have been found in deep Subaru HSC imaging. The images unfortunately do not have any labels because I don't know what is real and what is not. And so what I'm thinking about is to look for unsupervised learning in order to find clusters of various types of such sources, and hopefully, I have also injected a few simulated objects inside. So if we can find where these simulated objects, which cluster they belong to, then we may be able to develop an algorithm which will be able to separate out the junk from the real sources. So that's the idea. The data for this is available on SciServer, and I will tell you how to access it. Okay, so that's project 2. Questions? Yes.
So, usually in radio images,
Yeah.
there is also a problem of detecting artifacts as sources. And what we do is we invert the image because there is a symmetry in these artifacts which would not be seen in a negative pixel scale. Right? So that is how usually the artifacts are taken out. Can we do such a thing?
So it's something that needs to be tried out.
So these artifacts.
I don't know how that is done in radio, so maybe we can talk once during the talk sessions. Else, at least about the data or the problem. Solutions we can think about later.
So how much data is there? What
I have like 100,000 cutouts.
which is on Slicer one?
Yeah. It's like a 2 GB kind of data set. It's fixed images, but I have provided a script on how to go from fixed to PNGs. There are also lots of scalings that you can do, whether you want to put it in a linear scale or not, and so on. So that you can play around with in order to pre-process the data before you feed it to a machine. Any other questions? If not, then we'll move to the next project. Okay, let's move to the next project. So, Ashish.
This project involves the use of ZTF data. What we have been doing is that ZTF is the sky survey that takes data for all northern sky. And we have several hundred images of all of northern sky. And then the sky is divided into different fields. And it is these individual fields that get analyzed. So what we have done is that there is a paper on arXiv as of last week, which talks of these classifications using the system called SCOPE. And the data sets are on Zenodo because there are a large number of data sets that we didn't copy them separately to SciServer, but you can take one and put it there and play around with it also. So mainly what happens there is that there is this field _xyz.csv file per field, where xyz is a 3-digit number, and there are several hundred of these. Right now, only several tens. And this is essentially a CSV file, as the name suggests. What it has are the positions of the objects, some additional metadata, but a large number of classifications. We do many binary classifiers asking whether a particular object is RR Lyrae or not, whether it's supernova or not, whether it's pulsating star or not, whether it's variable or not. And one of the aims here is to get confident classifications and ambiguous classifications. This is a very general open problem. We have solved some part of it, obviously. But here what I wanted you to get introduced to is how some of the simple things that are there and how one can get into very complex things from there, because there are many deep questions that one can ask, especially related to subclassification using this. And that's why deliberately I did not put any Python script, because these are just CSV files. It should be easy to simply read the CSV files and start doing lots and lots of things there. And for each of these objects, and we don't have time series included, but the time series are also public. And then for the interesting objects, for the ambiguous objects, it should be easy to pull out cutouts and pull out time series. There are API calls for that, which are all very straightforward and documented. You can go into more details on that if you decide to do this. Any questions?
So the idea would be to get the time series and then...
No. So the idea would be to start with the CSV file. It has a large number of classifications. Because all these classifications are independent, one of the simplest thing to do is that get me all objects that are greater than 0.9 for one classifier. But then would the other classifiers also be claiming that object? If one of the other classifiers says I'm 0.5, plus there is some kind of hierarchy. So one of the classifiers that we have is variable or not variable. Then there is one that is periodic or non-periodic. So if you are looking for RR Lyrae and you have got 0.9 in RR Lyrae, then because RR Lyrae are pulsating and periodic and variable, so in that hierarchy, what you are going to see is that there will be high numbers there as well. So that doesn't contradict it being RR Lyrae. But if you pick another leaf node like Cepheid, you better not have that 0.9 also, because then there is some issue with the object, which may make it more interesting.
Yeah.
Right? So those are the kinds of exploratory things that can be done with this.
Okay. Sashish? Project 4 is the simplest. Nothing to be done. Next is project 5. So please put these project numbers in that Google form.
Do we renumber for project 4 or do we?
No, don't renumber, please, because it will get confusing. You have got so. Project 4 is not there. Point is, I would have to change everything. So that would be too much.
45 has two slides.
Yeah.
And then it's 6.
Yeah, more, but then I thought you have to wind up in one slide,
Yes.
so somehow I that's it.
And then 6. Okay.
Okay, so good morning all. I am Kaushal Buch. I work at GMRT. Since the last few years, we have been dealing with methods for mitigating online interference, which is a huge problem at frequencies starting from 130 to about 1 gigahertz. And so this is a kind of typical digitized series which you look at, where this is a noise which is of interest, this astronomical signal, and all these impulsive outliers which you see in this distribution are all because of sparking on power lines, transformers, etc. And this is there anytime you see in lower frequency bands, you will see this kind of a signal. And if you go into more detail of this, this has been taken from a high time resolution oscilloscope, sampling at 5 nanoseconds. You would see these bunches here, which would repeat at 10 milliseconds because of the 50 hertz AC cycle. It sparks twice in AC cycle, and you can see this. This is a 50 millisecond stretch, and you could see this sparking events coming as a bunch. And so the current solution which we have provided is to have a statistical filtering, which has worked well, which we have seen a lot of improvement. Now the second level which we want to go is to make that filtering smarter or to do more intelligent filtering of time series. But you can see here that the challenge is that if we detect the bunch, we could find the statistics of the signal inside the bunch. So it's easier to capture the bunch, and we need some algorithm which could smartly do it on a huge data set. But you can also see that there is a great variability. So this is on a different day, same source, you could see a completely different kind of signal, or a different band, you could see a completely different kind of bunching and the properties of the RFI within the bunch. So we could easily locate if the bunching was very nice, like the one which we see here, but it becomes difficult when the bunching is different. So we have data set. So I have provided one data set on Sci server where you would have this kind of a time series plot, and I have also provided a Python script to basically read that file into an array and plot it. And the thing is, it doesn't have labels because it's just, we have just recorded the series on the oscilloscope and given you this data. This data is huge. This 50 millisecond stretch is around 300 MB or so. So maybe if we want, we can get more data, we can put it. And the main thing is, once we know this, then we can zoom into the properties of this and we can see that how the distribution of the sparking events looks like inside this bunch. And then we can understand more about the RFI and come up with more sophisticated ways of filtering only the interference with minimal loss of astronomical data. So this is what I wanted to propose, and if anybody is interested, we can discuss more on this and go ahead.
I had a question. So what is the task that you want to accomplish?
So right now the task is to, in a given time series, identify these bunches. Because here is where we will come to know what's the exact property of the RFI.
Yeah.
So can we have some technique whereby we can easily identify these bunches?
So bunches you mean like T1 and T2, which tells you
Yeah, so I should get a boundary here that this is one bunch, this is another
Boundary
bunch.
in time.
Boundary in time.
right? So
Yeah.
T1, T2.
Yeah.
T1, T2 kind of.
And then I can see how much is the distance between the bunch, how much does it vary across the data sets, how much what's the duration of the bunch, and so on.
So here one idea is that working often if you convert time series into images like you have done here, convolutional neural networks are very powerful nowadays. So there are many strategies which involve converting data in other forms into an image and then using any number of image processing techniques or AI with images on this. So that can also be tried.
Yeah. Thanks.
Because visually we can clearly see. If you ask a human to
Yeah.
identify the bunches, they can just do it.
I think a lot, as we discussed a little bit about this yesterday, but a lot of pulsar techniques might also be useful because this is a cyclic signal. A lot of the, as Yogesh was mentioning, there is a lot of work being done on making images after folding them and then trying to use machine learning on that. So that might be interesting, even to look at the individual sparks which are happening and when they are happening, if there is any pattern, that would be very interesting.
Why can't just we take a Fourier transform, put it in the frequency space? It would automatically enhance the periodicity of it.
So maybe let's discuss the solutions later.
Right.
Because otherwise you'll get it. Okay, so I think that sounds good. At least the problem is known. Then we can think about this. Okay, thank you. Next is project 6.
Right, so hello everyone. Okay, so the project is a bit different. It is a safety measure rather than something to do with astronomy. But this starts from the project motivation started from one thing in 1930s when a certain guy called Karl Jansky was looking at statics in communication lines. Okay, and he found out that he was trying to classify these statics up, and he figured out that there were particularly these statics was caused due to thunderstorms, and he tried to classify these thunderstorms into various groups. And in this paper, which I have tried to link below, he classified it into 3 types of statics. One was a local thunderstorm. Other was somewhere there's a thunderstorm and we are trying to detect it. The antenna is detecting it. And there was one more source which he then later realized that it was cosmic, and thus radio astronomy came into being. Cut to 2021, when I visited Gauri-Bidanur Observatory. During that time, I saw that during such an event, the engineers from Gauri-Bidanur ran outside during a lightning storm to take out their RNAs and started to disconnect all their antennas. And I was quite surprised to see that there is no system in place in these observatories which would actually save these RNAs or save these costly equipments, which I think from the radio group here might be knowing that these RNAs cost quite a bit. And it could also, from further investigation, I found out that they also hamper the data. So yesterday we had a talk about RFI, and I think right now RFI is becoming a big problem, but this also causes a lot of RFI, and these RFIs could actually saturate the amplifier itself, or it could lead to some kind of a sharp millisecond pulse into the data, which I wanted to put forth as a question. There is no question mark there, but could this lead to a possible confusion with transients, etc. And so the way in which this slide is presented is something how I look at the problem as to how could we possibly solve it. We know that currently LOFAR is looking at lightning observations. They are doing some geophysical observations, and they have started to work on lightning maps. So from there, I figured out that what if we have a reference antenna, which could tell us what type of search is or what type of lightning is coming up. Then we could cross-match it with GPS readings or some other kind of reading. And then we could come up with possible classification of lightnings that would help us realize that, hey, there is a lightning coming up. It would warn the observatory, and it would tell the observer that during your observations,
this type of lightning was present, and you should not expect a very good data. Or possibly, one thing about RFI is that the sources are unknown, right? You do not know what type of things are causing a bad data in RFI. Possibly this could answer one of the things that during the observations, this type of RFI was present, and you should look at it carefully. So what if we have a trigger warning system where we classify, of course, classifying lightning would be a very difficult problem, but what if we classify the damage of it? Say that one damage, let's say black, is to just stop the observations because it could harm our equipment. One could be moderate, that let's say this could harm the observations in a very drastic way. And one could be that there is a lightning present, but the observations can still go on. But the observer knows about it. So this is a real-time warning which could be used for remote observations when people are not around. And this is what the case is for radio astronomy usually. So that's about it. The additional considerations are, can we make it real time? We should make it real time, of course. Then this would also improve the adaptability of the observatories to various environments, like upcoming SCA, which are in, or some of the radio telescopes which are in desert countries. And you know that whenever there is a desert country and there's a thunderstorm, there are going to be lightnings, lot of lightnings there. And what if we have a user-friendly interface to display warnings? A simple approach. Yeah, that's about it. Thanks.
So, what sort of data do we have already for this?
Correct. So, as I said, LOFAR has started to study these lightning maps, etc. One possible data set could be LOFAR itself, where they are trying to figure out these initial breakdown pulses, which I have highlighted there. They actually are trying to map the entire lightning process itself. Right. So possibly those could be one of the data. Then other data could be, there are these large stations. Usually whenever there is a lightning, there is a magnetic field associated with it. And there are a lot of VHF, there are also VHF sensors and magnetic sensors, which is a sort of a public data available, which could be used to classify a problem. So there is a real-time lightning map also available, where there is some delay between you and the observer, and we could figure out a way to finally get those warnings up. So the real data collection would be something that I would look forward to see. How could we do it in a better way?
So have you put any data on the Psi server?
Not yet, not yet.
Okay. Anything else that anyone wants to ask? If not, then let's move to the next
Thank
one.
you.
That's project 6. Oh, some images. I was trying to add. Project 7.
Hi everyone, I'm Saili Kulkarni. I have proposed that finding and classifying, am I audible, right? Finding and classifying AGB stars. So basically, when after MS means main sequence turn off, the hydrogen burning stops and helium burning in the core stars. The star expands and cools down a bit, increasing in its luminosity and becomes a red giant. When the helium burning in the core stops, the star expands further, the luminosity also increases, and it becomes AGB, asymptotic giant branch star. So these AGB stars are very rare to find because very less proportion of stars have become AGBs because our universe is very young. For all stars to become AGBs, the AGB stars are sites of S-process elements. Then they are long period variables. Long period variables are basically a peculiar type of AGB stars where they are thermally pulsating. The helium, when the helium burning in the core stops, the thin shell hydrogen burning starts again. it sets off for a short period of time. What it does, it prevents the inner leftover helium to come up. Then the helium gets built up for millions of years, thousands of years, or perhaps a million of years, and finally it comes. It tries to come off or tries to come out for a very short period of time in an explosive, aggressive way. It's called helium flash. So that is the thermally pulsating phase of AGB star. So in that phase, the helium flash process, helium flashing phase, the AGB star becomes long period variable. Then the AGBs are also, they have this kind of so the AGB stars lose their mass through stellar winds, and the stellar winds kind of attracts or accretes cosmic dust as well. So that's how they are there to find sites of S process elements, that means low neutron capture process, which gathers or creates heavier than iron elements. That's why they are important. But at the same time, they're very rare to find. So that's why we need machine learning. But before that, we need to create some data by some visual. There should be some human touch to it. So we can gather data with, we can find them rather with Gaia data. The Gaia data gets us the astrometric data with parallaxes and other stuff. Then we can have the other information on age and metallicities through the, because we have the open clusters data as well. So clusters age means we can find the AGB's age and metallicity as well. Then we can combine the Gaia data with parallaxes and what else? Okay, sorry. And combine it with the photometric data like 2MASS, and also with the help of spectroscopic surveys like SDSS, we can gather much information, very much, substantial information about AGB stars, and can have build the SED, the spectral energy distributions. And this 1D spectra, we can use as training for machine learning techniques. So I will need help with that because I come from astronomy background, so I know what the theory is, what AGB stars are, and how to find them. But I will need some collaboration. Thank you.
So questions. So what kind of data are we looking at here? So you are saying you will be able to provide 1D spectra of many objects, and we have to identify AGB stars from that?
No. We have model spectra for AGB stars.
Model spectra.
Because they have now, through the process and the dredge up processes, because this helium, thermally pulsating helium flash in this process, this is for first dredge up. The whole surface composition changes for a star. Then the core becomes now carbon and oxygen. Carbon and oxygen are in the core, while there are some shells of helium, some thin shells of hydrogen, leftover hydrogen, and something like that. So
you can give like model spectra.
Yes.
And then what do we have to do?
We can train perhaps we can train the machine learning, develop the machine learning techniques, train the machine, and we can then ask the machine where to find them. Like there are some limitations of human touch or human vision, human inspection, visual inspection, but we can then have more and more data. We can use other photometric surveys such as, there is one that I know, 2MASS, and then we can have some more.
Are there some identified AGB star spectrum?
Yes. We already have a catalog, not made by me, some other group, but let's not rely on that catalog entirely. Let's make first our catalog. Yes, let's first, we have to start from the scratches, right? So we can start with making a catalog itself. It would, I think, take 6 months or so, or maybe a year. I don't know, because nullifying the parallaxes from the Gaia data itself takes 2 months or so. Then we can get the open clusters, CMDs and CCDs. overplot them with the isochrones, evolutionary models like Padova, or maybe we can use Mesa, and then we can have luminosity cuts on them, and the CCDs and CMDs will be in Gaia bands itself, G band and then BP, RB band, BP and RB, the blue and the red one. Yeah, so that's how we know where are the AGBs, where the AGBs are lying in the open cluster that we have. So for example, if we take Milky Way, our own home, then we can put some parameters in Gaia first. We have the parallaxes. There is the script is given. Yeah, more details. Okay.
Okay, any more questions?
One thing.
Yeah.
You are trying to train on the spectrum, not trying to understand the periodicity. Is that or you?
Periodicity of the in the case of long. Okay. No. Yeah. Okay. So when it comes to classifying the AGBs, there are 2-3 types. First is early type of AGB stars, which use helium core burning, part of helium core burning. Then this comes this TP, the thermally pulsating that phase, and then there is this third phase, superluminous AGB stars. In that phase, the AGB stars are really luminous in infrared, those bands, and they become distinguished, or we can find them, not easily again, relatively, but relatively easily we can find them, locate them, so identifying is one part, classification is another one, and that is important as well. So we can find them, classify them using machine learning. First,
what will be period of this?
Sorry?
What will be period of this object? When you say long
period is with thousands of years. Thousands. So the helium builds up for thousands of years. The hydrogen doesn't let it out, but at some point, if the core pressure inside this of this helium element is so much that it comes out very explosively for a short period, but relatively short period, I mean to say. But it will cool down. It will take 1,000 years to cool down again. So during that period, that helium flash period, thermally pulsating period, the brightness will be so high, the luminosity will be much brighter. So we can use these features to locate and classify.
Okay, so that's project 7, I guess. Then we can move to.
Thank you.
Oh, now we go to project 11. Okay, sorry for this confusing numbers. Yeah. Yes.
Hello everyone, am I audible? Okay, so this is not something that I have already worked on or have a concrete work, but it's more of a baby idea and I would love to pitch it. So I'm a 3rd year undergrad at IUCAA Pune and prospect maths major. So I was really interested to use graph theory as well along with ML. So my idea is to cluster the pulsars and analyze that how similar they are to each other. So the steps could be, first, we can use the pulses and as an analogy, we can relate them to the vertices of a graph. And then the edges of the graph could be assigned weights, and the weights would, but before that we have to establish a minimum spanning tree so that we have all the vertices and there are no cycles between 2 vertices. And then we can assign weights to the edges, which would be proportional to some characteristics of pulsars, for example, radiation mechanism or their magnetic properties that can be derived from the PP dot diagram. So our basic and the only data set as of now is the PP dot values of the different pulses. And then using that, we can assign weights to the edges. And then we can apply graph kernels. So graph kernels are a kind of SVMs, support vector machines. But the idea is they use dot product between two graphs to establish that how similar two graphs are. So that is the idea. And furthermore, we could also establish a hierarchy that how similar are binary to solo versus solo to solo pulses, because the hypothesis or the idea is the binary pulses would be less related or less similar to the solo ones compared to binary versus binary. So that is it.
Thank you.
Thank you.
Good question. So questions about anything related to this project, the data, etc.
What is the number of rows that you
Okay, so I guess I got the data from NASA's government website, and it's 10,000 rows.
So there's no classification right now, right? This is unsupervised, I suppose, right?
Yes, unsupervised.
Does your data have binary as
Yes, they do.
Not the labels. They don't have the labels.
Some pulsars are in binary, some are isolated. So that classification is.
They include both of them, but we don't know that which is.
You don't have a label for that.
Do we know which one is binary and which one is isolated?
In the data set.
Okay, yeah, I think we do.
Oh, so there is extra.
Yes, yeah, there is. Thank you.
Yeah, very super. Okay, thanks. Project 12, Shreyash.
Right, hi everyone. So this project is again about pulsar binaries. So as we heard from Jayanta yesterday, there are a lot of pulsars in the galaxy which are yet undiscovered, and many of them are in extremely compact binaries. So if it is not in a compact binary, if it is far away, the pulsar pulsations don't change too much because of Doppler shift and so on. So you can take a Fourier transform or something called a fast folding algorithm to detect the pulsations. But if they're in extremely compact binaries, they're moving around very fast. It becomes very challenging to detect them because the pulsar signals don't actually come periodically. They get Doppler shifted very rapidly, even within your observation. So people do things like acceleration searches, jerk searches. So it's the derivative of acceleration. Acceleration itself changes during your observation. But that is computationally extremely intensive. And so we want to find all of these compact pulsar binaries, but we don't actually detect them. And it would be really nice to have these things because there will be sources for LIGO and so on. And we would want to detect more of these. So what we get from the radio telescope after de-dispersion and some pre-processing steps is a time series. You can see on the top over here, you just get intensity as a function of time. And there is basically no signal here. But if you know how the pulsar is rotating to a great degree, you can fold this data together and then the pulsar signal emerges. If you don't get this folding very precisely, this signal will be washed out and you will not detect it. So we often, after you get all the parameters correctly, you'll get a very nice signal. And you can see there is a pulsar over there. But finding this pulsar in a 8 to 10 dimensional parameter space is very hard. Okay, so but it is extremely easy to simulate. So the idea here is you have all of these pulsar time series simulators. So Presto, SIGPy, Proc, these softwares exist, and we can very easily simulate millions of pulsar light curves. But then can we use machine learning and something like transformers to look at very faint signals in this kind of a plot, right? When we have folded at some arbitrary numbers, but the signal should be there maybe in a blurred manner, and then try to estimate what the binary parameters are. Now, this is a very vague problem, but I think there is a lot to explore here. So let me know if you are interested, and we can talk about more of this. There are a couple of links here. So this is if somebody is interested in how pulsar searches are done. This is a good introductory link. And these are links for simulation codes. So you can just simulate time series data to a great degree. You can vary all the parameters and then try to back calculate, train a machine learning code to figure out what those parameters are. Any questions?
Yes.
So your training data set versus the simulations.
Yeah, so the training data set is just simulations, and you can create as many of them as you want. It's extremely cheap to create the simulations. It's computationally inexpensive. You just create it, and you're not limited at all.
But the noise realization, like I suppose when you try to train something, you will also have to include some noise.
Yeah, so the noise is already included in the.
It is already included.
Yeah, the simulators already create Gaussian noise.
Okay.
Obviously, so in many cases you can approximate it reasonably well with Gaussian noise if there is a clean signal. But you're right. I mean, RFI can be extremely non-Gaussian, and so we can start with the simple case where the noise is Gaussian, and then you can work into a more complicated system.
Any more questions? No. Okay. Thank you. Sushmita.
Hi everyone. So one of the projects I thought I would propose is trying to identify and characterize galaxy clusters using machine learning. So clusters of galaxies are essentially thought to live in these really massive dark matter halos that are about 10 to the 14 solar masses and higher. And the number distribution of these massive halos are very, very sensitive to cosmology, and other than that, there's a lot of interesting astrophysical phenomena that's going on inside these galaxy clusters. So one of the challenges in cosmology has been that assigning a mass and characterizing these galaxy clusters is actually quite an involved problem because, of course, we don't directly measure the mass. Oftentimes, we have tracers of the underlying dark matter halo mass. So oftentimes we rely on tracers to estimate what the underlying mass is. So particularly in an optical survey, we rely on optical photometric survey. We rely on picking up the clustering of galaxies to identify these objects. And typically, what we do is the galaxies that actually tend to live in clusters tend to be red and dead. So they're essentially low star formation galaxies which have little to no star formation, and they lie in the color luminosity. If you were to plot the color and luminosity distribution of galaxies, typically these galaxies lie in something that is called the red sequence. So they're typically picked out by identifying their clustering and this red sequence. But these methods are not, particularly for photometric surveys, these methods are not perfect, and there are these clusters identified in photometric surveys where we don't have spectra, we just have this photometry of galaxies, typically suffer from various systematic selection effects. So one of the things that I was thinking we could do is we could use machine learning to help us identify these objects. So essentially, what we could do is we could take one of these galaxy catalogs from one of the large photometric galaxy surveys like DES, and we could identify, we could try to feed different parameters of the galaxy data, including the galaxy colors in the different photometric bands, the positions of the galaxies, the local density around the galaxies, and firstly, in one of the methods, try to identify them, see if they cluster in this parameter space, and essentially in an unsupervised way to see if they cluster in parameter space, and then we can actually go back and check if we have other ways of identifying clusters, for example, using using the Sunyaev-Zeldovich effect, and we can try to see if our algorithm is actually identifying these clusters to the right places in the universe. And then we can try to estimate cluster membership from there. And so that could be one direction. And then the other direction is to use spectroscopic data from lower redshift to identify cluster members using their radial velocity distributions.
and then do sort of supervised learning to pick out these, let's say, sequence objects and identify them and use them in these photometric surveys. Yeah, so that's the basic idea. What I've put on Sci server are these DS, this dark energy survey galaxy catalogs, which have color, magnitudes, and positions. And I've also put the ACT, which is an SD survey cluster catalogs on the Sci server. I haven't yet put spectroscopic data, but that is available and we could put that there as well. So yeah, so this is the basic idea of the project.
So the ACT catalogs are from the SD effect.
Yes, the ACT catalogs are the SD.
So is it correct that all of the ACT cluster catalogs should have a counterpart in DS?
In the DS footprint, they should have.
Because the selection from are mismatched. So
ideally they should, but there is it's not like every one of them have a counterpart in the DS. So they are tagged, the ones which do have it. But we found that sometimes some of them are missed.
So, so the machine learning will have to identify cluster position.
Yeah, so I think in the unsupervised thing, I think first I just wanted to check if it can identify clusters of galaxies in this parameter space, and are we identifying it correctly, right? So that we can use it in different, like an LSST.
So just with photometric data, you want it to identify?
Yeah, just with photometric data and density information around these individual galaxies, can it identify things which, the members that belong to a cluster, for example, right? Of course, how we say what belongs and what does not belong in the ACT to get.
No, I'm still trying to think like what would be the input data. So
yeah.
Like if I do a cutout, like a random cutout, take all the galaxies from there, is there a cluster here or not? Or tag each of these galaxies?
So what I was thinking is, for every galaxy, I have their location in the sky.
Yes.
And I have their color, magnitude, and all the other information.
Yes.
I also can estimate sort of a local density for every galaxy.
A local density.
Yeah.
Okay.
And then I put that into a machine learning algorithm and see firstly if it finds clustering in this space, and then try to see if that actually corresponds to.
Yeah, but it still needs to know
distances.
Yes.
So the position information should go in, right? So that it will find actual physical clustering as well. In addition to that, if it finds clustering in color.
So the input data cannot be just one galaxy.
No.
It has to be multiple.
It has to be. So any technique,
that's why
will have to take into account the fact that
how you need to pass in multiple.
What do you mean?
Because you still need to give a bunch of galaxy information.
Yes.
So that it can identify whether there is a cluster and
Yeah.
which are. It needs to standardize how to get that input.
Yeah.
Okay. Okay. Any more questions about this data set?
So instead of providing the individual, instead of looking at clustering of, let's say, individual galaxies, could we in the parameter space where we will be looking for clustering, could we assign like regions of space there instead of one galaxy? Like let's say identify the clustering of spatial, compute the spatial clustering of.
Yeah, so I was thinking to do the spatial clustering and this extra parameter space together, right? So I wanted to pick up the spatial clustering as well. Maybe I need the.
Yeah, so I guess we can, one goal would be in the next few hours, even come up with like what.
The algorithm.
Yeah, what exactly you want as an input, as an output. Just having even the mapping can be helpful. Yeah. Okay. Okay, good. Thanks, Sushmita. Project 14, Divesh.
Hi everyone, I'm Janki. Okay, so now we have placed this project is about cosmology and we are shifting from data to simulations. So the idea is that we have this time period called the epoch of ionization, when the first sources ionized the neutral hydrogen in the intergalactic medium. And we have very few data available to constrain this time period because we only have lower redshift data from CMP and Diamond Alpha Forest. So what we actually, how we study the time period is basically mostly simulations, and we need to have a very large dynamical range for the simulations because we need to simulate the astrophysics of this time period, what were the sources, the galaxies, etc. And we also need to know the large scale field, the IGN. So basically which parsecs around like hundreds of megaparsecs. So we need from hundreds of kiloparsecs to hundreds of megaparsecs dynamic range for this problem. But that's very difficult with computational resources which we have available. So we need to use super computers, etc., which has been done actually. But there is another approach to this, and that is being recently explored, which is called the super resolution simulations. And for that, the idea is that we actually have some high resolution simulations available. And then you train a machine learning model on these high resolution simulations for a given set of modeling parameters. And you see what is the statistical patterns, what are the patterns of ionized regions, etc., which is coming with in the high resolution simulation. And then for a wider range of modeling parameters, you try to create a higher resolution simulations by only providing lower resolution simulations. So that is the idea. And this idea has been explored, but only by very few groups and only using very high computational resources, which we don't have. So the what we are proposing for this project is that we have available data. So we have 10,000 simulation boxes, and as a proof of concept, we are only going to use a 16 cube resolution for smaller boxes, which is on the right hand side, and 32 cube boxes for the high resolution one, just as proof of concept that for how well we can reproduce this 32 cube boxes. And so what we don't know what machine learning architecture we'll use, but we will try to figure that out and we can discuss that. So we will basically train our machine learning model on some of the data which we have, and then try for a different set of modeling parameters which it has not already seen, and then try to reproduce, see how well this matches with the high resolution simulations. Both the simulations, the statistical properties, as well as what just comparing pixel to pixel. That's it. So that's the idea.
Thank you. So,
so currently we have both 10,000 cubes, but because we have 16 cube and 32 cube, these are just a few like boxes. That noise.
I mean, what is the statistical?
So currently there's no noise, but when we try to reproduce the large boxes, we might get some of the. We need to have at least some of the statistical properties. For example, the power spectrum should match. The non-Gaussian functions like bispectrum should match, but that will come later. At first, we can just check by pixel to pixel comparison and see how well that matches.
When you downset the
Just we can just average it out. So it's not. We are not adding any noise right now, but we are
sample there is no information.
Yes.
To create not exactly.
Yes. So the idea is to basically create the better resolution simulations given just the modeling parameters. That if you have a certain kind of modeling parameters, for example, if your halo sizes are small, so it should be able to be that.
So, I mean, universe has a statistical link between these large scales on which you are smoothing things. No, but I think it's not just because these are low resolution runs that will be, they won't even be able to resolve the small scale structure. So there's no averaging being done. It's just I mean, the simulation itself does not know the underlying. Yeah. Yeah. Different underlying. So it has to learn how, like how these large sediments are connected to the small things, so that it can fill in the small things.
Have some, basically, I mean, if we assume this laboratory model,
Okay. Any more questions? Yes. Oh yeah. Okay. Can you hold it close?
the data. Okay, so we have a script is basically a code which generates the ionization boxes very fast. So we have used script to generate 10,000 boxes, both of the lower and high resolution, and then we are going to use some of them for training and then the other for testing.
So can you correct me if I'm wrong? Okay, so you will have like 3D positions and some property. What is this color? Say XH1, right?
Yes, XH1.
Right. So it's the ionization fraction. No.
Yes,
This is a 3D matrix.
3D, yes. So it's a 3D box.
Each cell has a ionization fraction.
Exactly. At each XYZ, there is this value. Okay. And there is a box which is done at high resolution and at low resolution. The idea will be to go from this 3D box at low resolution to a 3D box at high resolution. Right?
Yes.
Okay. You had a question? Yes.
So this is kind of upscaling algorithm, right? So normally in let's say video CCTV footage, they do upscaling. Then what is important is we know the human features that are exactly similar. Like face will be like this for all the humans. So is it same like if you change the initial parameters, will the features be same for the higher resolution model?
No, that will depend on
the large scale features will be same.
Statistically,
yeah.
So, I mean, if you change parameters completely, your simulations will look completely different. But you know that universe has certain properties, that we have certain metal power spectrum, etc. So there are certain constraints, but we don't know the exact details. So that's why we are simulating those details. And so large scale features are going to be the same for both the lower resolution and high resolution, but the small scale ones are which they're trying to learn. That's why we need to.
Okay, let's move to the next one because we have one more thing before we go on to that. So yeah. That was what was the number for your first? 40. Okay. This is the last one, I think.
So, hello everyone. My name is Pooja Maji, and I am a research scholar at NCRA. So, I mostly try to understand the low frequency solar emissions, which are mostly related to space weather. And I mainly use the Australian telescope called Murchison Whitefield Array, and so these low frequency emissions that I work on, which is basically the type 2 solar radio bursts, these are very highly variable with time and frequency. So if you want to understand these emissions, so you need to understand these emissions in very finer time and frequency resolution. So with NWA, we make the images with a cadence of half a second and with a frequency resolution of 160 kilohertz. So and these images, so for an example, for a 8-minute of image, like 8 minutes of data, we get 500,000 images. And to give you a sense of those images, like how rich they are in struct features. So here is one example. So this is a Stokes QU IUUV images. So there you can see that in the second image you can see multiple positive and negative components all together, and then in the third one you can see multiple positive components, and so in the fourth one also. So understanding these features in the whole 500,000 images is a very difficult task for us. So what we want to do, and there we want to introduce the ML, because we want to understand these images, these structures, their positions, their sizes, their locations, changes, evolution with time and frequency, and therefore we want to introduce ML in that. Now, talking about the data structure, so let's suppose that that red rectangle is showing source of the emission on the solar disk. So that is the theta and that is the phi axis. So here we want to make a 5D hypercube where one axis will be the theta and phi, which will be showing the locations. Other axis will be the Stokes polarizations, I, Q, U, V, and the other two axes will be time and frequency. So this will be the data structures, and we want to understand the evolution with time and frequency and their locations for these structures. So that is the idea. Yeah.
Yeah. Questions regarding the data. So this you already have uploaded to Sun server, or you can make it available?
Okay, so the images are available, like the images we have, but we don't have in them in this particular structure. But
so you need to convert it.
Yeah, but it's an idea.
Yeah, sure.
Like we don't know how to deal with this kind of.
Okay, yeah. I mean, you can brainstorm with few people to get it. Okay, thank you.
Thank you.
Any other questions? If not, then yours. I forgot what click. Hello. Hello. Okay, so we'll quickly go about quick prototyping. Hopefully that will help us.
So I was asked to talk about some quick prototyping so that you guys kind of get a general sense of everything. So these slides were prepared in HAST, and what I'm going to talk about is also prepared in HAST, so bear with me. And you can ask questions, obviously. So a lot of times in real life situations or real research or industry situations, you don't get a really well-defined or scientifically well-defined problems. You just get a problem, and someone is working in some field, which could be really anything, and they come to you, and they have no idea about anything. They just have a problem that they're facing, and they're asking you to solve that problem. And so they're all obviously very open-ended problems. And my day-to-day is kind of dealing with and finding solutions for those types of problems, which are not always related to space research, but could be anything, mostly related to some government agency doing something. So one feature of it is that there's no label data. No one has really took the time to label the data or find labels for that data, because if you take a step back, they have not even thought about if you could do machine learning or any type of statistical reasoning or prediction or inference or anything like that. So no label data. There's also no data. So you're like, what do I do here? This person is giving me a problem, but they're like, we asked, oh, so do you have any data? They're like, I don't know. You tell me. I'm like, how do I tell you about? So it's a real situation. So we try to understand what their background is. Sometimes we try to find data. Sometimes we ask them questions so that they could locate data within their organization, educate them as to what kind of data would be needed for a certain type of general machine learning. So they try to find that data. And then we start thinking about how to label that data. Again, first you have to define your problem itself, then you go to that, but let's just talk in general terms. Label data could be mined. If it doesn't exist, there could be ways in which you could use some pre-trained model to create more data. Sometimes it's easier to mine data by writing a script. So as we saw 2 days ago, that just by predicting the next word, you could also train something that could do any art detection. So similarly, you can mine data for one particular type of downstream task, but in the process can learn to do other downstream tasks. So we can't be very picky about what kind of label data we want. Just some label data as like that could be fast arranged, and it's okay for us. And there's also no problems. If the person tells us this is the situation they're facing, this is the kind of, and they can say a large problem. For example, US Geological Survey told us that they do surveys and it takes a long time. So can you use machine learning to do the surveys? So it's a pretty open-ended general problem, and we had no idea what surveys are in the first place. Being at we do NASA things, they do geological survey things, and we were like, so what do you do in surveys? Like, how do you actually do the survey? So there was not really. So this is a general problem. It's not a machine learning problem. It's not like a small bite-sized problem. So after talking for a while, you actually try to see what the actual problems are that are solvable. So that's kind of the features of open-ended problems in general. So it's literally like pulling a rabbit out of a hat, creating something that didn't really exist before. But after a while of frustrations, maybe a year or two of frustrations with seeing enough number of these things, you start getting sense of it. And then you can maybe suggest things pretty easily. So how do you really proceed in such situations? So you should always have a clear idea, or if it's a vague thing, then you should bring it to some measurable things, like what is your objective? So this USGS problem, can you do the surveys? We could ask, why do you want us to do the survey? Why do you want machines to do the survey? Then they can say it can reduce cost, it can reduce the effort, and it can improve efficiency. Now those things are measurable. If the cost is reduced, if the effort is reduced, it makes sense to me. Then we can start thinking what in the survey we can do which can reduce these things. So you're going towards a specific problem from this vague statement or general description of the problem. You can see, or they can say, we want to optimize the process. Again, that was a trick point. It's very vague again. It shouldn't be like optimize. Like, what do you mean by optimizing the process? Again, it should reduce the cost. It should reduce the effort. Again, even those things are kind of mid-level. They should further be like reduced to some low-level, specific, measurable things. Cost is a pretty big one in US, so it should be something tangible, and then you can move forward in that. So you bring the problem to a well-defined one, even if the problem is general problem, but it should be a well-defined problem. Now, once you have the problem, you have to accept that you cannot solve everything. Don't bring your ego there. You cannot solve it. However big an institution you are, however good in ML you are, you cannot solve every aspect of the problem. So you start thinking about what can be solved. Okay. Again, in mental health, the therapists tell you when you have a lot of anxiety for future, you want to give an exam or something like that when you're a student, or something like that, even in like jobs and things like that. You have a big problem, then there's certain things in the future which you don't have control on. So you have to focus on things that you have control on, and you start there. So similarly, anywhere else, and here too, finding those nuggets which you can solve would be much more useful. And then once you have this list of like 10 or 20 things that you can solve in this bigger realm of this general problem, then you ask yourself, is it still useful in reducing my cost, reducing my effort, and things like that? If it's not, then you probably shouldn't solve this problem at this point. Maybe you should have some other approach. Maybe this is too immature of a problem and things like that. But most of the time, you'll still find things that you can improve upon, you can automate. So moving further, once you have the list of things that could be solved, you have to do some deeper analysis into it. You have to do some market analysis, some research. This is the kind of the exciting part, which I love. You go see who has implemented what so far, where is the current state of art. Sometimes it's a domain where you don't know what the state of art is. So you try to read a little bit, you backlearn a lot about that domain. You become experts within a month. And you try to see what has been done. These days, it's really easy over the internet to do this kind of analysis. You have to be really comprehensive, thorough. Try to go for the best papers. You can move backwards from those, what other techniques have been implemented. So you have to do more or less a thorough market research of what has already been done, because there's a chance that you propose something and you implement it, and then you realize that someone has already done it and is selling it, as an enterprise solution, or someone has a code online for it. So you don't want to do that. So you have to be thorough, or you have to also see what problems are too difficult to solve. The state of art has not reached there. So the solution will lie somewhere in the middle. Things which have been already solved, things which are too difficult to solve. So you want to propose something that's in the middle. If it's a research project, if it's an implementation project, then you have to first suggest some of the low-hanging fruits from what has already been done. Maybe it has not been done for this particular data, right? Maybe the client doesn't have a workflow for that type of problem. So you say, the things are available, but I can build it for you. I can do these experiments for you. I can do the evaluations for you. There's a lot you can contribute. So the idea is, how do you be most optimally useful to this task? Okay. So you don't have to be experts. You have to be useful in a lot of situations in data science. Now you have to think how feasible it is to implement. If you want to implement something, how much time, how complex, how optimized my code needs to be. I love this part personally. How optimized my code needs to be. Over some years of experience, you learn when to optimize your code, when not to optimize your code, when to write really well-defined classes, and when to write scripts. So those things you need to take into account based on how big your projects are. Idea is, be useful, be impactful. Don't spend too much time over something that is not going anywhere. So, and then obviously, how will I evaluate my progress? Are there metrics? What are people doing for this type of problem? And a lot of times, the problem is so new that you don't have a well-defined metric. So make sure that you don't you don't just slap a metric that has already existed and it's just taking you nowhere. So try to create a metric that is solving one of those high-level objectives as well. So that if you have a low-level objective evaluation, it doesn't relate to the high level, and at the end of the day, when you're presenting it to someone, they're going to ask you, how is it then reducing my cost? And you're saying, it's reducing my loss function. Is it not good for you? Good enough for you? It's not good enough for them. So keep that high-level picture in mind always. So that brings us back. That brings us to why all this. Always have a mind for prototyping if you want to be parallel with data science, or if you want to go into data science. Think about prototyping as much as possible. Technologies change so fast that you want to do quick things, you want to prove your concept, and then you want to invest your money and time into something. Find is the word. Don't implement first, find it. So find implemented solution. Don't try to reinvent the wheel. Again, don't have the ego of an expert that I'm going to implement the best possible code for this. If someone has done it, try to update it, try to see who has done it, what kind of code it is. It's also a great skill to understand something that's already been done in coding, rather than creating your own is sometimes easier, but then the problem you'll face is while debugging it, right? And then you'll be like, I should have used the person's code. It would have taken me maybe a day to understand what they had done, but it was probably already debugged to some extent. So try to find solutions that other people have done. Be part of communities where you're not duplicating effort. You're using things, you're producing things that other can use. So collaborate, overfit. Whenever you're developing a workflow, when you're developing a model, try to overfit on your data, because that's how you know that the model, the idea, the architecture is even able to learn this problem. So first try to overfit, then try to learn and like improve upon the test set and all that stuff. You can find a lot of those things, but try to see if it actually works beforehand. Don't spend 6 months and then realize that this is not going to work. I'll use some other architecture. So these things, these searches, doesn't have a lot of complexities, so that you can try your architecture really quick. Because if you're not an expert in training machine learning, then you might face a lot of challenges that you will have no idea. So if your data is simple, then you can follow through and see how it's being changed, backtrack it, and improve upon your architecture or move to a different architecture. So again, don't jump to something very complicated in the beginning. Slowly do that. Again, try avoiding rabbit holes. There's a research rabbit hole. So when you start researching for implementation, you always find something that looks cooler than what you're doing. And it keeps on happening because papers come out every week, every month, and there's always someone who's doing something really amazing. Don't keep jumping from things to things. Implement something, then improve on things, because then you'll not go anywhere. Although you will get a lot of experience in a short amount of time of what's available, but do implement things. Don't keep jumping. Bring yourself back to something more tangible that you're doing. Technology progress rabbit hole, I guess it's the same thing. As we are implementing things, technology is developing in parallel, especially with foundation models and LLMs. So in that case, I'll give you an example. Me and Ashish have a student, and we asked her to implement a workflow for domain adapting large language models for question answering tasks. Now, she was very confused because she's like, there's so many great models, and isn't your task to give, aren't you asking me to find the best model that is going to work on your data? And so basically I corrected her, like, we don't care about the model, which is because there's always going to be a new model that we can fit into and use it. Our task is, can we create a general workflow where if a new model comes along, we can plug it in. and test our whole architecture. So if we have ground truth ready, if we have the process framework ready, and if we have the evaluation ready, then you can plug and play any new technologies, but have that general framework workflow ready in data science and machine learning. So have whatever you develop in a pluggable way. So things could be plugged, and you don't have to do, reinvent every time. So self-duplication, don't have to do that. So that's kind of it. If you have any other questions, we're happy to answer.
Thank you. Thank you. Okay, so then we can break for tea, and then we'll come back here again and divide into groups. Yes. You. Right. Yes. So there's one quick thing which is important. So many people are putting in data sets that they have access to and can share with you, but it should not go beyond this group. Okay, so just remember that. So if you get access to some data from us, from SciServer, then just check with us whether it is okay to share in case you need it. That is an important thing to keep in mind. There are some data sets which are public and then it may be okay, but first check with the person who has shared the data with you whether it's okay to share. Okay, so then let's break for tea, and after that, So after that, I will just show a quick demonstration of SciServer, and then we can divide ourselves into groups, and we can float around also if you want. The URL for Google form to choose a project is written down. Yes. So let's come back by 11:45.
But then again, you need labels. Some machine can do some.
Yeah, so I saw you can have this few projects. Yeah.
I haven't done thousands.
That they first try by using audio. Audio signal. Train a machine. So then if you try to trick it, even if you do something yourself.
Oh really?
Unless you are really good. So this idea is the request, which is the technologies for image classification, image identification, much evolved, much more advanced than try to identify audio or let's say convert everything.
As an input in this selection, and then for a variety of sets of parameters, and then try to do that based on different sets, and then we calculate for these different set of cases. In future, we can. Can you just put you in work so I can see your class?
येत आहे का सोबत? येत आहे का?
Machine learning will able to identify the pattern. What will be government?
Varun reading on me. Sheldon, that's actually right. Alien. Yeah. 8. 8. Yeah. IG. And then let us move later. Thank you.
You're in. Now you should be able to post. Don't put any attachments. Those require approvals.
Okay, okay.
So put a link. Attachment type.
A hyperlink maybe on my drive.
Hyperlink to the drive.
Yeah, not 10. Yeah, of course, we cannot solve everything in 1 hour. Yeah. Yes,
I was wondering if the conversation will only go through the mailing list, or we can even start.
You can set up your own alternative thing like Slack or whatever, but mailing list is useful where you don't know the answer to the problem within your group.
It's a general thing.
It's a general place like, okay, this is our problem. Does anyone have any suggestions or ideas? Maybe at the start of this, I'll just say a few words about it.
Maybe you can also say if you put in the project number in the subject ID.
Yes.
Then it also reduces, like people can easily find.
Anyway, the list is archived.
So you can always check.
All emails are archived. So one can go back later on. Okay, this question was answered 6 months back. So let me check in the archives.
Oh, interesting. So the link to the archive is in the same page that was there.
There is.
I remember there was an archive.
There is a link where you got you have been added to the mailing list. That email will take you to the mailing list page,
which has a link to the archive. I read something.
Antenna system. So maybe this is also something along the line. I don't know. Okay, so that is okay. So let's get started. There will be a quick thing that Yogesh wants to say about mailing list.
So we have set up a mailing list. Okay, most of you would have gotten email saying that you are added to the mailing list. It's called Astro Data Science. Those of you who are not on the mailing list but want to get on, please get in touch with me. I just added someone here a few minutes ago. The mailing list will be active indefinitely. The mailing list will be active indefinitely. So please use the mailing list as a sounding board. So if you have some new idea, for a new project, etc., describe the project in as much detail as you can. Describe the data that you have. Describe other things about the data, and then hopefully there will be others with more experience who will respond. So all of us, all the resource persons for this workshop are also on the mailing list. So we will respond, we will give you some ideas, some suggestions and so on. And we'll also use the mailing list for educating ourselves. So for example, I've asked Asitang to send a list of resources. So there are a lot of books, review articles, online courses, etc., which will help us advance our knowledge. So he will be posting a list of resources with links to those online materials. So all of those things are there. So please use the mailing list. For today's work also, if you want to use the mailing list, that's an easy way of communicating. To avoid cluttering other people or people who are not working on the project, you can give as the subject line the number of your proposal, project number 3, project number 5, etc., so that people from your group will immediately see that and access it. The list is, email sent to the list will be archived indefinitely. So if a question is answered once, you can go back later in time and say that, okay, let's figure out, you can access the archives. The link to the archives is there on the mailing list web page. Okay, so that's all.
Thanks, Yogesh. Okay, so then we can already see that people voting on different kinds of projects, so that's great. And because you are sending also the site server names, the leaders for these projects, if they have downloaded some data, they will be able to share. Okay. Thank you.
So let's quickly go to the demo for site server. So I'm assuming that all of you have at least opened up an account on Sci Server, because that is the simplest thing to do. You can even use your Google account, I think, in order to log into Sci Server. So that's not a problem. But once you log into Sci Server, then this is the kind of interface that you get. And in this interface, you can see the activities includes files, then the groups that you belong to. So in principle, the group leaders can create a group where the users who are deciding to contribute to a project can be part of. Then there's this thing called compute jobs, which allows you to run either a Jupyter notebook or a script and send it to the Sci Server computers. They will give you access to something like 32 cores. And so with these 32 cores, the script can start running and produce whatever answers you need to get from it.
So both synchronous and asynchronous.
Yes. So these compute jobs are typically asynchronous. So they get assigned to a queue, and then as the resources become available, then your thing will get executed. So there are certain limits on the amount of memory that you can use, otherwise your job gets killed, etc. So that part you have to keep track of. And then there are science domains. So these science domains also have other data sets that you could use, like observational things or simulated data sets, etc., that are also part of this science domain. So that you can explore by yourself.
So you have joined one domain. What domain is
No, that was this simulation domain, but that is not required.
Okay. But these science domains contain data which has been preloaded.
Which is public and is preloaded, yes.
So like SDSS, for example, would be...
Yeah, so there is a cosmological simulations domain, and it has lots of different cosmological simulations and the databases, etc., which are available. Okay. Right. There is a genomic science domain, the manufacturing science domain. So there are multiple domains. So let's first look at files, because this is where we'll be uploading things. I have lots and lots of folders here, because whenever I teach a MSc project, I ask people to code, and then they share the code with me. But typically what you will have is only this persistent and a scratch directory. Okay? So persistent directory is the one where your data will remain. If you create any data or if you create any script, they will remain in this persistent folder. And then the scratch folder is if you have large amount of data and you want to put your data in it, then it will go to your scratch folder. Okay, or you should upload it to your scratch folder. So let's see what is there in my scratch folder. So in my scratch folder, there are many things, but I think the main thing important for this project, for this particular workshop, is this cutouts folder, in which I have kept these tiny cutouts. So this is a list of huge number of fixed files which are there, and this will take forever to load, so I'm not even going to go there. And the amount of files that are there is, it's like 2.4 GB. And so there's a huge amount of data that you can store in this scratch folder. Just be careful, if you don't use the files in that scratch folder or access them, then after a certain amount of time, these can get deleted automatically. So that's the part that you have to be careful about when you are doing things in Scratch. Okay. So if you need to upload any of these files, then you just go to upload here. It will ask you whatever files you need to put in, you can upload. And it will just, it's a simple drag and drop interface, which is also available here. So that should allow you to upload these files. And once you upload these files, you can share this particular directory with whoever you want. So this Scratch folder, for example, if you go here, then you are able to share this Scratch folder with any of your group members. So you can go to the groups, you can select who you want to share the Scratch folder with, and then those people will have also access to the folders that you're trying to share. So that is about the files. Let's go back. Now, let me tell you something about the Jupyter Notebook interface that is possible. So once you open the
So before you go there, suppose data is fine, sharing data, but you can share Python notebooks, anything else.
Yes, yes. So in that folder, you can keep whatever you want to share. Then that get.
And suppose multiple people are now trying to edit the same Python notebook. Does that work?
No, you give a read permission, not a write permission.
Okay.
I mean, you could in principle give write to, but then you have to worry about all this. So then on the Psi server, there is this thing called compute. So this is what you use to analyze data with interactive Jupyter notebooks. And there are multiple languages available: Python, R, MATLAB, etc. We will deal with Python, of course, in this case. So once you open this, you can create something called a container. So if you create a container, it will give you basically a Jupyter notebook. Okay? So in this case, I have created a container for this data science workshop. So I will just go to that container. When you go to the container, you will see a standard Jupyter notebook-like interface. I can even switch it to Jupyter Lab so that I get terminals and all sorts of good things that come with Jupyter, which are available. So it takes some time to open sometimes. So just bear with me. Okay. So anyone who has used Jupyter Lab, this again interface would be familiar. You can launch these terminals. I already have some terminals which I have launched. Sorry. Yes. Yeah, so basically, if you launch a terminal, let me show you the terminal that I already have launched. Notebook. It's taking time to launch. Maybe all of you are on Psi server.
Perhaps it is not happening to you only.
Yeah, I think it's my network. So let me just reload this thing. Sorry about that. Because when you try to do things on the fly, it doesn't. Okay, so let me at least show you the Python notebook that I have created for my data set. Okay, so this is the example Python notebook, for example, that I had created. So typically with these Jupyter notebooks, you already have things like TensorFlow, Keras, and many of the standard libraries are installed. If you need to install something else, then you can go to those terminals in the Jupyter Lab and do pip install, and it will still work. Okay, so.
And that pip install is not persistent, no? It's only for that container. You'll have every time you launch the notebook, you'll have to install those.
Yes, that's right. Every time you launch a container,
yes,
within the container, it will still stay installed.
So long as you don't close down the container, you can come back.
As long as you are not closing down the container, it should not be. So you can do the pip install. But anyway, so once I don't know why it is not opening for me, but once you do that, then so here, for example, what I've done is I have made a list of all the fits files that I've had, and then I'm giving example code which shows how to go from these fits images into these kind of PNGs. And I'm just right now, just to show, I'm creating a gallery of PNGs. In reality, when you have to feed in this data to do any unsupervised clustering as is required for my project, then you will take these PNG images separately and try to feed them together. So that would be the idea, right? So you can see some of these images, how they look like. Some of them, they are clear like sources. Some cases, they are not at all clear. And basically, it is junk, right? And so the idea is to separate out these junk from things which are the real objects, okay, in this particular project. So what I'm hoping is, with this short introduction, I've at least told you how to upload the files, create Jupyter notebooks, how to install libraries in case they are not already available, and create this kind of example Jupyter. And if you face any trouble in terms of sharing, etc., like how to share things with other participants, then SciServer also has a help, which you can see here. So if you go to your main SciServer page, click on your username, you will see here, help here. And so there is a lot of documentation. So you go to user guides, it's just one single page of user guides, and it will tell you all that you need. So how to share things, how to access any of these things that I've talked about. So I will just stop here because I don't want to take up more time.
One small question
Yeah.
is the sort of default resources that they give you. Are they large enough for solving a practical problem?
So they give, right. So let's see, large.
Storage anyway, you can put in Scratch where there is a lot of storage.
Yeah, storage is not a problem. So let me show you what they give. So compute jobs, synchronous jobs. Yes. So here's what they provide. So shared environment with up to 5 other jobs. So this is the small jobs domain. So you can submit either to a small jobs or a large jobs domain. The small jobs domain has 32 cores, which can be shared with other jobs. But 32 GB is dedicated to your job.
Okay.
And maximum execution timeout is 1 hour. So if you keep things like what is it called, like resets, right? Then you should be able to run it multiple times, right? So just make sure that whatever you run, if it is not going to finish in 1 hour, then you have appropriate checkpoints.
Yes.
Okay, so from where you can restart as well. Then there is a large jobs domain. So there the execution timeout is 8 hours, but 240 GB dedicated RAM you can get, and up to 32 cores. Of course, getting queued, so you may remain in a queue for a longer time on a large jobs domain than on a small jobs. So that is the game that you have to play.
Larger time meaning if it is like 1 month, it becomes impracticable. If
So
it's 6 hours.
my things are typically run fairly quickly, so I'm not worried. I have worked with students in a ICTS school where we use this framework to do things, and it was okay. But again, I mean, it all depends upon the job that you have, so it cannot be guaranteed.
Are these GPUs supposed?
I think there are only CPUs right now here. There may not be GPUs. So, like you can do the prototyping here, and then later on you can move on to GPUs. Okay. Any other questions? I guess not. So then maybe we can get started. I could see that there were already like people had responded.
Now, are the leads for each project, are they able to see the output of the Google form, or?
No, I can share. I'm going to share the Google Sheet basically.
You can share it with everyone.
Yeah, I can share it with everyone.
Can the Google form have an option of multiple projects?
Yes, in principle, you can submit. I have not restricted it to one response at a time. So in principle, if you open it again, you can respond. That's not a problem. Okay, good. So then maybe we can break into smaller groups. Some, like we can take one section there, one section here. A few people can gather around in the Kund area if you don't like AC, of course. The weather is quite pleasant, so it's not a problem. And then there are areas outside.
Can I look at the sheet right now?
Yes, yes, yes. So, sheet.
What you are sharing?
Oh, sorry. Right. Get this link. Yeah, yeah. Okay. So basically what we have is email address, which project do you want to contribute to, and the size server. That's all.
Is it possible to sort on C?
Oh, you want to know what do you want to know is the question.
Sorting on C, like how many assigned.
Oh, yes. That information I have. Just a moment.
The summary.
Yeah, I actually have the summary, but I just need to share the others. This is what it is. Yeah. So there are quite a few people who signed on to various projects, so that's great. And then there are certain projects which have many participants, so maybe those are like the obvious things that we can cluster around for them. All depends upon what you want to do. We will have this room available until 3:30 p.m. So that I have made sure. So even if you want to work a little bit more after the lunch, that is also fine. Should we keep a small wrap-up session around 3:30?
I won't be around there.
Oh, you are not.
Yes, I think that would be a good idea.
So let's see.
I don't know how many will be there.
Yeah. But anyway, at least the rooms are available, so we'll see. I may also have to go for some small things. Okay, so then maybe we can just divide into these groups and then get started.
Some are very small and some are very large.
Well, if there is only one, and I suppose is this only the project lead or not, that is also another thing. So I would leave it up to you, like what you would like to do, rather than try to dictate it from here. That if there are only two people, even they can brainstorm. So we are not expecting a lot of code, of course, to come out, but I'm hoping that at least for the time being, when you are here, you can familiarize yourself with the data set. You can try to understand if there are particular tracks that you would like to take, like if there are things that you would like to check papers, as Asita mentioned, where this kind of a problem may have been addressed, see the technology that they have used in order to understand and make a list, for example, of things that can be done. Okay? And then you can start coding on it, or you can start to pre-process the data. Things like this, you can get started with. And then, or even brainstorm initially about this. What are the approaches that you need to take? What are the goals that you would like to achieve? And the tangible aspects for this particular project, etc. And then that should be a good enough thing to start off. And then when you go back, then you can continue working with this. You'll either communicate via Slack or whatever you are more comfortable with, or the mailing list. Okay, so I'll stop here.
Then people should just go to the people who had announced the project.
Yeah, exactly. Yes. So project 2, maybe we can sit in that corner.
Maybe all people who propose the project should come to the front.
Yeah, come to the front. Yeah, people who propose come to the front, and then after that we can. So I will stop the streaming now because now nothing is. That was good.
Yes.